This is a talk that's completely not comprehensive. You can take gazillion courses that will teach you this material probably much better than I would. This is just stuff that I learned through time that I found was very, very helpful for graduate students working with me or other people in terms of what to look for and how to do, just simple rules as to how to approach analyzing data. And it's logic. There's no one way to do anything. It's just how I think about data when I come to analyze it. So please interrupt and
Did you remember to turn the thing on? Because I turned it off.
I did. Yes, I did.
Okay.
It's on. So statistics is the discipline concerned with the study of variability, with the study of uncertainty, and with the study of decision making in face of uncertainty. So this is what statistics is, and this is why we want to use it. It's a science of collecting, organizing, analyzing, and interpreting data. So why do I care about statistics and what you should care? I mean, if you give your data to somebody else, they can get the same result you did. But often we do what's data reduction. Rather than give them all our data and say, you compute the mean size or you compute whatever you need from it, we report an average size, how much it varied, things of that sort. There's different kinds of data. I mean, there's what's called nominal data, things that are not ordered. For example, taxa in EcoTaxa, the software we use to organize the images, each has a name, and we put these images, we try to sort them into those. There's ordinal data, which fit categories that are ordered. Like, in this case, they said as no objective measure, things like pain level. It's when you go to the doctor and you say, I got hurt, and they ask you, or to emergency room, and they want to know whether they need to treat you immediately or they can leave you there for 2 hours, and they ask you what level of pain you feel. And if you say anything 7 or below, you'll sit there for half a day. And then there's scale data, which fits things that are ordered with units of measurement, units such as meter per second for velocity or anything else. I mean, these are just definitions.
Emmanuel?
Yes.
The fan is on back here, so can you just talk a little louder?
Okay. We can also close it if we want there. So why do we need statistics? They help us provide answer to questions such as what's the concentration of plankton at the dock right now? Or will species X be in the water tomorrow? What's the likelihood that that's going to happen? We're interested in the likelihood of the answer, and I'll produce large data set into their salient characteristics. So I don't have to give you all my data for you to appreciate. About the use of statistics to make a point. Statistics never proves a point. It says something about likelihood. So you're not providing any proof. And this is one of the best advice I've ever given when I was a graduate student, is the fancier the statistic you use, probably the weaker the point that you make. If you don't see it, obviously, with very simple statistic, your point is probably very, very weak. And you're not impressing anybody but using some special tests that nobody else knows about. It doesn't prove anything about your wisdom or anything else. And the more fancy statistics you have to find to get some signal out of your data, again, probably your point is pretty weak. Just remember that. So you start with the population that's out in the field. You do sampling, you get a sample. Then you get some descriptors out of these, of which you do the statistics. And then you try to infer something about the population you started with. That's kind of the chain of reasoning that we go through. Okay, so typically we go and measure and compute some, as you did for the size distribution we worked with yesterday. We're trying to compute some statistical descriptors. The simplest one are things like mean, variance, so how far are things deviating from what we defined as the mean. Standard deviation, which for a normal distributed data contains 68% of the data within 1 on each side. If it's 3 on each side, it's 99%, square root of the variance. And we have something called average deviation, so that's and all these are what we call parametric statistics. These have meaning with respect to distribution only when you know something about the underlying distribution. Standard error of the mean, it's how much, so I calculate the mean, but how much is this, how well do I know this guy? Well, if I have a lot of points, I know it better than if I know, a lot of points mean n is my number of points, that if I have only 3 estimates of that mean, then my uncertainty is much larger in that mean. So this is the uncertainty of the mean, the standard error of the mean. Again, this is assuming that you know that it's normally distributed. Now, there are cases where you cannot reduce this by taking more samples. And those are really the hardest cases we deal with. So from all these, so this is a classic way in which people describe or teach errors. So this is, what you're seeing here is repeated measurement. When you're right in the center is your true value. And these are your measurements. You often don't know the true value. Which of these situations is the worst, do you think? The first stop here?
No, the left.
Exactly. This is the most worrisome one. You have an extremely precise scale. It reads 3 points after the grams. You think it's awesome, but it drifted through time, and you think that simply because you have a high precision, you're doing really great, while you're off by much more than your precision of your instrument. This is the most dangerous situation. And it's often the one we're dealing with. Our radiometers read radiance, wonderfully in terms of precision, but we're often not where we think we are. So this is the one, and here is where we bring always Rumsfeld, because it's the unknowns. This situation, you often don't know that you're biased. And if you have one instrument, and some people say it, and I cannot believe they say it. So my colleague, they always say, take one instrument to see. Because if you take 2, you'll not know which is right. Right, this you'll have yes, Colin.
My technician, Sue, says the person with 2 watches never is sure of the time.
But he has a sense of how wrong he may be. With one watch, you're sure of the time, but you could be significantly wrong and you don't know by how much. That's exactly the point. So if you have if you have the possibility to have more than one instrument, take them with you. If you have them in your lab, take all 3 of them. At least from time to time, you can see what variance there is in between them and get us. And if all were calibrated at the same time, it will give you something about the drift of your instrument. So this is where you want to be. This is our hope. This is not too bad because if we take more measurement, we can get closer to the true value still by the square root of n law. But square root of n law is not going to help us with any bias. It's never going to correct a bias. Now, we can test for biases by doing what we call closure. And we started talking about closure. There'll be a whole lecture about closure. And that's the idea. If you try to get to the same answer from 2 independent directions. Can it be with model? You take a model, you put all your IOPs in, you calculate reflectance, you measure reflectance in the field. How close are they? If they're very close, you have more confidence in both of them. If they're apart, you don't know which one screwed up, but there might be a problem. Or you're doing reflectance with the 3 methods that we learned about, and you see how close they are. And the further away they are, the more uncertainty is in. So the more you learn something about what might be the bias, you don't know in which one of them, but associate with the method. So really, it's your best friend. Your best friend is closure. And I review lots of paper, and in most of them, people don't do closure. Why? Because they have one instrument. And they don't even try to see if the relationship between the 2 instruments they have, say beam attenuation and backscattering, is consistent with what you would expect. You always want to do it. If you measure turbidity and backscattering, there is some relationship between them. It might be with significant differences, but large uncertainties, but there is some relationship between everything we measure. You measure in the open ocean chlorophyll and you measure POC, there's a relationship between them. Again, there might be, it can change some, but we know that. So you want to compare all the different pieces of your data set with each other and with other people on the boat that are measuring something else for their own purpose but have similar instrument, just to make sure that you know something about the magnitude of this. It's really, really, really important. Okay, so description of data, it's exactly like what you did for size distribution. You can do it with any data in terms of what's the distribution of this data that I measured in the field, my chlorophyll. You can put it in different bins of values. In this case, it's the frequency distribution of the height in inches, a very scientific unit, of 24,000 US Army males. So in this case, it's pretty good normal distribution. But it could be extremely skewed. This is age at death. Doesn't look like normal distribution. There's obviously a mode, a mean, a median, but they're all different. And if you don't know the underlying distribution, you might make wrong inferences from your statistics. An example is chlorophyll or POC or even SPM. Do you have a sense of how it's distributed on the, if you took measurements from all around the ocean? Any idea? SPM, chlorophyll.
Long tail?
Long tail, I mean, obviously it cannot go below 0. And it's very often distributed in something that looks like log normal. And there are a few papers from a woman named Campbell, Janet Campbell, who was a program manager also at NASA, that have looked at that, have looked at the distribution. So this is something you may want to do in your lake, in your area that you work with. Just put all the measurements and see how are they distributed, because that will help you when you're trying to describe the variation and variability. So when you don't know the underlying statistics, you can rank your data, just organize them by how high. You can do the median, which is the one in the middle, 50 percentile. You can do percentiles to describe variability around that median. You know, for example, if you wanted an equivalent of a standard deviation, you'll go from 14th to the 86th percentile and divide by 2. That will be your equivalent of the standard deviation. You can carry the mode. That's the one that counts most often. If it's relevant, it's usually not relevant to what we do. And the nice thing here is it's very robust. And by robust, I mean it's not sensitive to outliers. If you have a very large value, it can throw your mean very far. But if you use a median, it's not going to change the median at all. My Bible in everything numerics is called Numerical Recipe. It was published by Press et al. It comes with codes in C, in Fortran, in Basics even. But the text in between those programs that they provide is extremely valuable because it's designed for users. It's for engineers, I believe, that wrote that book together, and it's really practical. How do you go practically about fitting curves to data, all that stuff. So a lot of what I'm telling you, I'm channeling my numerical recipes, what I read in numerical recipe. So robust means insensitive to small departure from the idealized assumption for which the estimator is optimized. So for example, you might have a measurement where there's a really obvious central peak associated with your culture, size of your culture, but there's also a lot of stuff. There's a tail of due to precipitation in your culture. There's all this, but you want the size of your diatom or your size of your Donaliella or whatever. However, if you try and look, so if you just use everything here, you might be skewed out of it, particularly if you calculate volume or things like that, because these might have a large volume. But on the other hand, you don't want to go and say, okay, I'll remove all this data because I know it's noise. Because sometimes you don't know that it's noise, and it might be important, might be relevant, or might be something you want to keep in the graph, even though, so you don't want to throw it away. So there's methods, same with fitting lines, and we'll come back to it, that if you used a least squares fit, just like you usually do, will give you a very different line than the one that by eye you'll tell, this is the line that is most consistent with my data. Now, why would least square fit give you something that biased? Why do you think it is? When you have a few outliers running around here. It not only takes in account outliers, it squares the difference. It's trying to minimize square differences. So it will try much more, it will put much more weight to a point here than any weight that's close here, because it's much further away. Now, why do we use least squares? Why do you think we use least squares? What's special about least squares that people like to use it? From my perspective, there's only one reason. And the one reason is, before we had computers and you wanted to fit a line, least squares allow you to derive the slope and the intercept of the line for least squares by hand. You could do it by hand, because you can differentiate a cost function that's least square. You cannot differentiate one that's absolute value or square root or anything else. So it's just what they used to do. And we're keep doing it. Why? Because this is standard procedure. We don't think, we just do least squares because everybody does least squares. Seriously. So the point of view of this lecture is really to have you think, is this what I should use? Why am I using it? What's the reason? You don't have to use least squares. You can say, I used a cost function that minimizes absolute value. And this way, this one will weigh more than this one by distance. If I wanted, I could do it in a square root sense. So it will weigh, so it will not weigh as much. It will be the square root of the distance that's going to be weighed, et cetera, et cetera. Okay? As long as you report how you did it, there's no problem. It's true you cannot use, most black box fitting routine will do least squares. And so you want to get away from using black box if you can and do your own cost function and your own fit. It's not that hard. So here is an example where I was diving with this AC9 on my back. There's a coral reef here. There's sand right next to it. From time to time, I'll run into canvas on under the same waters. And what you see with beam attenuation, for example, as you dive just above the reef for the sand, there's much more spikes above the coral reef than there are when you get above the sand. So there's a difference between the mean here and the median. These are the probabilities for beam attenuation at 440, just a distribution, above the coral reef and above the sand. So there's something on the reef that's different than the sand, and I can get information by looking at this distribution and these large big spikes that occur on the reef, which might be associated maybe with large particles that are made of goo that is released by the corals, or maybe it is zooplankton that are there. I don't know. Typically, I would assume that next to the sand there will be resuspension and maybe more spikes, but no, that's not the case. Here is doing dives 2 meter above bottom, 50 centimeter above bottom, 10 centimeter above bottom. And what you see in all cases, as you get to closer and closer to the bottom, there's more rare large particle. And it appears there's a difference between the mean and the median, a bigger and bigger and bigger difference. And you can see it in the data. If this is something of interest for you for the process that you're interested in, then looking at these different moments of the data is useful. Again, it depends what you're after. So why do we care about, why in research we care about statistics? It tells us something about the relationship between variables. Do we get blooms, for example, when there's a lot of nutrients? Is this when we're trying to infer causation, even though it does not tell us about cause and effect? Contrast between condition. Who dominates when we're near a river, etc. So that's where, now, we often look at linear linear correlation where we're trying to relate two variables. Again, this is in parametric, but we can also do it in order. You don't have to do it in the value. You can also order data and order the other data and look at the ordering and whether those are related. And then then you're less dependent on what it means in terms of your underlying distribution. So this is a really cool case. I have a textbook on statistics for atmospheric scientists. These all have the same mean, standard deviation, and correlation coefficient. All of those. So it's worthwhile often to not just calculate your statistics, but look at your data. See how it's distributed so that you get a sense of what does it describe. These all are okay? And apparently it's called Anscombe's quartet. It came from some paper that the guy concocted exactly this to show people that what you can have. Okay, regression models. We often have, when we regress, even without thinking about it, we have a dependent and an independent variable. Our independent variable is what we put on the x, and our dependent variable is what we put on the y. For example, an absorption spectra, the absorption is the dependent, the wavelength is the independent. Or time series of scattering. We have time and scattering. But what about chlorophyll versus size? Which one is the dependent? Which one is the independent? Typically when we do what's called model 1 regression, we assume all the uncertainties are due to one parameter. This one we know perfectly, and all we're trying to do is minimize departures in this direction. But if you do chlorophyll versus size, for example, or whatever, chlorophyll versus POC, these are both extrinsic parameters, both depend on concentration. We have errors in POC, and we have error in chlorophyll. This is really, if we put errors on everything. So how would you fit a line to those, or any model, to something like this? If again you go to Excel or you go to your general package, it does a regression by only minimizing the uncertainties in the y direction, not in the x. It's assuming the x has no uncertainties. Anybody knows what regression that take into account uncertainties in both are called? Type 2. They're called type 2 regressions. And these are your friends. Because if you did a line here, and then you inverted POC versus chlorophyll and did a line, they're not going to be equivalent. Yes, typically.
About type 2, we talk about calibration of fluorometers. So you have an uncertainty in the 30-second reading of your fluorometric, of having your fluorometer in the bucket, and then you also have an uncertainty in your chlorophyll estimation. Right? Because you should have done triplets, and you would have propagated your error there. So when I talk about type 2, it was exactly this question right here. You don't want to overweight, or don't not weight at all both sets of your observations, because they're both have observational error.
And in your regression, of course, you should take uncertainties into account and not just use the points when you're doing a regression. So you should have a regression where the cost function to determine what the regression is takes uncertainties into account.
You can imagine that each one of those data points has some sort of distribution about it, right? And if you actually prove the distribution of data that went into each of the means or medians, that actually should be impacting that line.
And if I have one point that has a big uncertainty, for whatever reason, we do the wrong bottles, this is how it comes, I don't want to throw it away, but I don't want to weight as much as the other ones for which I have smaller uncertainties. So I can keep it in, but just weight less. And in order to do that, this is still a type 1. I have, for type 1, this is for least squares, I would have the uncertainties in my y. So this is for type 1, again, a spectra, I will have these uncertainties, but points that have big uncertainties because I'll put their uncertainty here, are not going to weigh as much as points that are having small uncertainties. So I can still have all my points in, but take into account the fact that the ACS, when I feed a spectra to the ACS, rather than throw away all the data below 450 because it's much noisier when I go below, I use that noise in my fit, and then I'm still okay. Okay, so we can usually, we should do it regularly. And we're finding that it makes a difference in our result if we do, compared to not doing it, with fitting all kind of function to the AC spectra, as an example. If we have errors in both X and Y, you can accommodate both of them in your fit. So now again, if you want to do least square, but you can also do absolute value. You can do absolute values here as opposed to. You don't have to do the squares. This is a book that I found at my father's when I was a kid. It's called How to Lie with Statistics, and basically the idea here is that if you really wanted to, you can pick, people would pick and choose the statistics they want just to make their data look better. And so you have to be very cognizant of it in your own work. So variance does not explain, is not explained by anything, although people say the percent variance is explained based on your R square. It does not reveal cause and effect. It is very strongly affected by dynamic range correlation, the correlation coefficient. So when you have a data set where unfortunately you sit at one place for 45 days in the North Atlantic and everything is like this, and guess what? We're going to get very poor R squares for exports because we did not have a few points here and a few points here that then will make a beautiful regression. But our ability to predict X from Y has not changed at all just because we have more R square. We can still say that, when this varies from this to here, we can predict that from there to there. That has not changed, our ability to, but we don't have a good R square. So for me, what I want to know is, what's your error in predicting one from the other? Don't tell me your R square. I want to know how well you can predict A from B in your model. 20%, 30%, plus minus 2, whatever. But that for me is of much more interest than you'd give me R square, because I know that R square can simply change by adding 1 point for, in coastal environment where I have a lot of signal. Everything looks good. So. And similarly in paper, if all the statistics you give me is your R square, I send you back home, I'll do type 2 regression and tell me how well your model, what's the uncertainty in your model prediction compared to what you actually measured. Type 2, slope of type 2 often is the geometric mean. There's several ways to do type 2. Geometric mean of the two different slopes that you get when you do Y versus X and X versus Y. We don't have to get into it, but there's a nice set of MATLAB routine on Mbari's site where you can get those routine on how to do type 2. It do type 2 for you, and you can change for yourself the weighting function if you want it to be absolute value, square root, or anything else. We often have reason why we want to smooth data, because noisy data might not be very useful for us. The noise might be instrumental. It's electronic. It's just the fact that there's variability in it. But some of it might be environmental. If you put your sensor in your bucket that you took from the dock, you might have a very stable signal. Yet if you put it over the dock, you're going to get, because water is flowing around, you're going to get the variability that comes with that. And that could be part of the signal you're interested in. And always remember that what's your noise may be somebody else's signal, and there might be a whole science associated with it that could be or not interesting for you. The classic example is the atmospheric correction. We correct for the atmospheric correct for the ocean. And it was really fun in PACE meeting because each other's noise was each other's signal. In MATLAB, I like to use something called filt. It's a boxcar that runs back and forth, and of whatever size you want to have it, and it doesn't phase shift your maxima. But obviously it's going to, whenever you use any smoothing, you're going to reduce the maximas and increase the minima, so you have to be aware of it. You always want to compare your smooth signal to your original signal, and does it make sense for you to do, and report what you did. We used X. As we said, the method of fluctuation is all built on this fluctuation. This is the noise that you want in order to infer size. The method Briggs did. So in this case, it is your signal, the noise in the measurement. Why do we model data? It helps us to condense, summarize data by fitting into a model that depends on some adjustable parameter. For example, for the CDOM spectra, we have something like this. For particular attenuation spectra, we have something like this. This is not what we measure, but then instead of reporting a whole spectra with 88 numbers or 83 numbers from my sensor, I can report just two values, the value at lambda naught and this value. And if it's a good fit, that's all. I have only two free parameters to describe the distribution of in my paper. I don't have to give you 88 wavelength in every paper I write, which are just not independent. There's a lot of redundant information, possibly. With the absorption of particulate, some people do Gaussian fits, and you get those Gaussian out. So how do we fit? There's two things we want to know, the amplitude, the slope here, and we can build a merit function, a cost function. So we have our model, we have the uncertainties here, we have our data, and we're trying to minimize this, or again, we can do it absolute value. Usually I like to use absolute value. And again, we can weigh wavelength in the blue less by putting their variance in our measurements as part of the weighting. Yes?
Can you explain the condensing of data?
Yeah.
A little bit more?
So as you saw for the CDOM spectra, it fits really nicely an exponential curve. If you report it, you can report it graphically by providing spectra, all the spectra you collected. But it's very hard for me to get a sense of it could be hard to how variable it is. But you can provide a distribution in your paper of the amplitudes. These are my amplitude at 440. This is my AG at 440. And this is my slope distribution. And this might be around 0.014 nanometer to the -1, the center of it, and how much it varied around. This is useful for a variety of things, but among them is also for people to have I want to have confidence in your data. I want to know what kind of slope distribution you get. Is it something consistent with what we see in the literature or not? And if not, why is it not? It might be you discovered something new. But it's just a way to condense data. Instead of you showing me just spectra and spectra and spectra of everything you measure on which you're going to do science, you're just showing me the salient feature of your CDOM. And that's sufficient to describe the whole spectra in the visible.
So it's still graphically, but just
it could be graphically or it could be in words. You can say our amplitude at 440 varied from 0.2 to 2 with an average of 1, and my slope, the slope fit to our data varied from 0.01 to 0.02 inverse nanometer with an average of 0.015. Okay. It can be just in the text, and that's, but it will tell me your slopes, because I know about slopes of CDOM and I care about them, that these are reasonable slopes, and that you're in an environment where CDOM varies by this amount, which means light getting to the bottom might be that amount, et cetera, et cetera. So, okay. Yeah. Instead of you having a table at the bottom of with all the data you collected, which nobody wants to see, and there's no room, et cetera. But you'll put it in CBAS, and somebody who wants to can go to CBAS and find that data.
And then it's a lot easier to compare across labs, right? What was your slope? What was your gamma? And as long as everybody's doing the calculation the same, then you can say, oh, it was a steep slope, it was a flat slope, instead of having to look through everybody's figures and track figures.
Yeah, well, it's consistent with what I would expect. It's not. Maybe there's interesting science, or maybe there's methodological differences, but this is how. They use a different filter. Instead of 0.2, they use a 0.7. That will make the slope less. Things like that. So again, you can, whatever you use, you want to say in your paper how you fit. I did a nonlinear fit weighted by the uncertainties, minimizing the absolute values of differences. Fine. And the uncertainties were based on 1 minute, a variability of 1 minute of the spectra. Great, I know how you did it. And then I know if I want to compare quantitatively to what you got, I know what I should apply to my data to do that. Now, for nonlinear model, there's no guarantee to have a single minimum, just so you know. So nonlinear fits, you have to provide a guess, and that guess, whatever minimizer, use that guess, and goes from there to find the minimum. And so, depending on how complex the model is, this one probably, there is only one and it's the minima, but in other cases, you can find multiple localized minima, and there's some schemes that are more or less robust in getting to the global minima. Yes?
It's a good question about the uncertainties. Is it like uncertainties that you get when you're measuring, or the standard deviation of all of your measurements?
So, I mean, it's for the whatever data you're interested in, and it's your best guess to the uncertainty as function of wavelength. If it's constant, you don't need to put it. It's going to use them. It's going to weigh them all. This is the part where you're telling this cost function, there's some wavelength that I trust more than others. Or if it's some data set, you can put here the standard deviation. If it's, I'm trying to fit, let me think of an example when I'm trying to develop a model for chlorophyll per cell as function of irradiance here. So I have, and usually the higher the irradiance, the smaller is going to be my chlorophyll per cell. Irradiance I know really well. Maybe I have a small uncertainty in it, and when it's dark, but I have some points that have large uncertainties. I don't want this one to drive the curve. Let's say that this point is here, but it has a large uncertainty here. I don't want this point to force the curve to go like this. So, because I know it has a large standard deviation, I'm going to put it here. And it's not going to weigh as much as these 2 points in my model. And I don't have to throw that and say, oh, any point that had a bigger standard deviation than X is not part of, we threw away. It's not a good data. So I can keep my data on the graph. I never throw any data out. I show everybody the glory and the misery in my data. But my model is robust because it takes outlier into account by weighing them less. Okay? So that's the purpose of doing this weighing. And in MATLAB, the F-mean search is often it's a Levenberg-Mercat, but there's different ones to do fits to model. So here we talk about the more robust merit function if I do absolute value or anything else. The problem was in the past because derivatives were not continuous, but that's not a problem anymore. And when you do that, as we said before, you get the line you'd expect without having to sacrifice or throw data out or come up with all kind of reason why this data is bad. It might not be bad data, and it might have a lot of science associated with it. And you might learn a lot eventually from it. So this is a great text that I decided to put here from Pete Humors about reporting and propagating error. So practicing science well requires comfort with error and good judgments of its magnitude. Otherwise, there's no way to tell whether observation fall outside prediction from an alternative hypothesis. So this is the way by which you determine if you discovered really something new or whether what you're seeing is consistent with what other people have said. Science makes the most progress when ideas that seem reasonable are discarded in favor of better ideas on the basis of data. So if measurement error is too large and sample size too small to distinguish which idea is right, science cannot move on. So we need to be able to determine if indeed our numbers are significantly different, and if we throw everything that doesn't fit our preconceived model, we'll never discover anything new. In science, error is a necessary fact of working with physical evidence rather than something to be avoided. It is uncertainty in measurement. Here we'll assume that error and imperfection are identical. The only way to know about inaccuracy is to have some alternative measure. So this is again going back to closure, which is not universally the case. Moreover, when two methods disagree, it is not always clear which is the more accurate. Our best measure of inaccuracy are against known standards, because those standards have been tested thoroughly. So this is what we're going to do this afternoon in terms of calibration, is using something we know in order to try and make our instrument be what it should be. But that's, I mean, it's standard also in the field, and it's standard, it's when you're looking at the sky with your sun photometer, you know something about the sun because many people have measured it many, many times. We have a sense of what we should be seeing in a perfect clear day, and you can say from that whether your instrument maybe has a problem. A little bit about propagation of error. How many of you know about all these? I mean, do I have to get into it or not? You know, I mean, obviously there's a group that has done errors and they've shown us that they know how to do error propagation, but is this something that you guys covered in graduate school or undergrad? A bit? So basically, if you know your uncertainty and you have a relatively simple formula on then you can, for a simple formula, I mean like x divided by y or x plus y, you can have a sense of what the uncertainty in the combination is. So let's assume we have two variables and they're related by some function q. Okay? And our x has an uncertainty. It's the true value plus minus delta x, except that we don't know what xb is, the true value. But we know it has an uncertainty. It's within a certain uncertainty from our measurement. And the fractional uncertainty, it could be also a fractional uncertainty, which is delta x over x. So that's the implying that this is the uncertainty. So a small number of rules. A small number of rules serve you well for most purposes. If you're simply adding x and y, the uncertainty is a square root. If it's x plus y or x minus y, the uncertainty in the sum will be delta x squared plus delta y squared. What is the assumption that we're making when we're doing this? That these uncertainties are not correlated. So the uncertainties in these are independent of each other, which is a strong assumption. Otherwise, we would have to add 2 delta x delta y, which is the correlated part. So we always throw that out. Most times we throw it, unless we know that they're linked. So this is for x plus y and x minus y. That's my delta x plus y, or delta q, or x minus y, I can put here. Now, if it's x times y, or x over y, the uncertainty is as follows. So if this is my q, x times y or x, delta q over q equal square root of delta x over x squared plus delta y over y squared. So the relative uncertainty is the root mean square of the relative uncertainties of my variable, where q is x times y or x divided by y. Okay, so this is this one. And if it's a power, and we know that power exactly, then it's simply n times delta x over x. And then in general, it's really a derivative. You get there, the way you get to these formulas is from taking the derivative with respect to your variables. So it's dq dx, delta x plus dq dy, delta y is my delta q. And then I square in all that. So this is where these type of formulas are developed from. It's just first derivatives to calculate the uncertainties or the deviations. But often we have, so these are simple models, x plus y, x divided by y, these are very simple. But what do we do when we have something like hydrolyte, where there's many pluses and many division and many multiplication and many things like this? What do you think we do then? And we want to put in a radiance that, an IOP that we measure, and we want to put in also uncertainties in these IOPs. What do you think we would do? Yes?
You run a Monte Carlo simulation, right? So you get a range of possible values as uncertainty.
So you have a distribution. So you know something about your distribution of IOP. And let's just take one here, for example. Let's assume, we need to put in we want only 440, and we have an absorption at 440. So we'll have, this will be our frequency distribution of this parameter. And these are the values in meter to the -1. And randomly, we'll choose a value, put it into hydrolite. And then another value, put it in hydrolite, another value, put it in hydrolite, as well as for all the other inputs we put into hydrolite. We'll weigh them by the likelihood they're going to happen. So we'll weigh this one, the output from this one, more than the output from this one or this one. And then we'll add them, we'll look at all the output we get, and we'll do statistics on that. We'll get an average hydrolite prediction for remote sensing reflection and reflectance, and then an uncertainty around it. Exactly, and that's what we call the Monte Carlo.
When you say, like on this example, that you'll weigh the values where the thing, what that really means is you'll do more runs with absorption near the mid value, and there will be an occasional run with a larger, smaller.
That's one way to do it. Or if this was the only parameter, you can do, if this is the only parameter that changes and not everything else, you can do 1, 1, 1, 1, 1, 1, and then weight by your absolutely. So here is an example. We typically have a lot of variability, and with a lot of parameter, we'll run them all through, weigh them by their likelihood, and get a variety of output. And this is how we look at a black box where we don't know the relationship, the functional relationship necessarily, or we don't want to deal with it because it's too complex. This is the lazy approach. The only problem with the lazy approach is you don't know what you should expect. And the nice thing with these formulas, these explicit formula, is you can see if it makes sense what you're getting as the uncertainty, but given what you gave it as uncertainty in your individual parameters. Yes, Kurt?
In the case of, let's say, doing evenly spaced A values, but then weighting the output according to the magnitude of the distribution, I can see that would work if the output is linearly related to the input. But if A is in there as some squared thing or whatever, then it seems like that would not be the way to do the, you should just do a lot of runs rather than a sequence of runs and then weight the output. Because that would properly take care of a nonlinearity, especially if you don't know what that nonlinearity is.
So what Kurt says, which is better than what I said before as an approach, and you're right, is you use this probability to choose your value. You fit it into your code. So you choose a random number. Usually you can, in MATLAB, for example, you can tell it what the distribution, and it will choose a random value if it is Gaussian or if it is uniform. So if the probability is this or the probability is this, you can tell it. And it will give you a value from 0 to 1 for different distribution. And then you'll say, okay, if it's 0, this is my value, 1 is this value, and for any discrete value in between, you're going to map this distribution into it with the most likely one, and you'll tell it something about also your standard deviation around that. So you'll either that or you'll normalize your probability distribution, and then each time you get a number out of your random number generator, tell you, okay, my A is now this, or no, my A is this, or my A is this, and that will go in. And then my B, similarly, et cetera, et cetera. Ken, you want to say something?
I was just going to say, the nice thing with the splitting them apart and not just throwing it in a Monte Carlo is then you can also see where is your big problem.
Yes.
And try to work harder at that. There's a lot of uncertainties that probably aren't very important, and there's no point working on those, but there's going to be one or two that are driving everything.
We'll have, in Monte Carlo, they have an exercise doing exactly that.
Excellent. So you'll do this with Hydrolite. Bootstrap, so these type of Monte Carlo. One of the things you want to know, for example, is what's the variability what's the uncertainty in S? If you don't take the log of the data and try to do a line on it, it's really hard to know what's your uncertainty in S unless you're putting in your variability in the measurement and trying to fit it again, variability, trying to fit it again, variability, trying to fit it again, run it 2,000 times, and then see how much your slope is sensitive to your uncertainties in your measurements. And again, you can wait if your wavelength are noisier in one or the other, you can put it in, and you can use absolute value, etc. So this is all possible to do. So to summarize, there is no right and wrong. I mean, use statistics logically. People abuse of it, or use it in ways that make sense. What you want to do is convince yourself and the people with whom you share the data that what you're describing is the salient information about it. If you don't know anything about the underlying distribution, use non-parametric. You don't prove anything with statistic, but it gives you much more of a sense of a likelihood of a hypothesis or a relationship. And I further suggest for you to study things I did not talk about, things like hypothesis testing and Bayesian methods. This, in particular, is now becoming very important. And Bayesian are one where you look at conditional probabilities. So rather than assume that everything is uncorrelated, it is likely that when you have more chlorophyll, you'll have more PRCs, and maybe you'll have a diatom there. So you might want to use that knowledge as part of your model buildup. One last thing is that there's a lot of literature recently about the use of p-value. A lot of time you'll send a paper in and people want to know what's your p. It's the good p, it's the bad p. So tons of information, tons of things about misuses. They found that more 50% of paper used p-values incorrectly. So just for you to know. So it's yeah. Yes, Ken.
So last two things. One is I gave Sasha a document to put up there it's called the Gov. It's the government or the something uncertainty on measurement. Guide to uncertainty on measurement, put out by the Committee of Metrology from International Committee. It's the fundamental thing that guides how you should treat uncertainty.
And it's
how to
really
do
well
it.
written.
And it's
Easy to access.
so it is the Bible for it. The other thing, which is totally off, is I have a whole bunch of growlers back here. Some of I think they're growlets, I guess they call them. I can't remember. There's an oxbow growler. There's a Booth Bay. They don't do this anymore, so there's a Booth Bay brewery growler. If you want to go to Oxbow, you wash these out. They've been in my closet for a couple of years. Wash them out. They'll fill them up, not for free, but they'll fill them up.
But it's significantly cheaper. Usually they're like $3 redemption value. These are.
Yeah, so you can bring, anybody can take these. The one thing is I don't want them back. I was told I can't bring this home. So you can leave them out and you can grab whatever you want, take home for a souvenir, whatever you want to do. I don't really care. It just is not going back in my book. So there they are.
Any questions on any of this, either the beer or this, before we? Yes, Colin.
I would reiterate about the gum. And it really, we had a really incredible presentation about at least about how to report uncertainty and how to report uncertainty, but all the very different ways that you can assess it. And it's really clearly expressed. So if it's a topic for you